Hello, welcome to this supplemental video on using the free SpectraPlot tool to model and plot the absorption and emission spectra of gases at different temperatures and pressures. This is a supplemental video from my course on global warming and the greenhouse effect. The lecture script is available at a link given in the description of this video. I recommend that you follow along in your browser and pause the video as you go. Go to website www.spectraplot.com. No registration or login are required. We can click on Absorption, Emission, or Line Survey. In this video, we will start with absorption, and we will use emission at the end of this video. We will not use line survey, but you may like to try it. Click Absorption. We see the plot of absorbance versus wavelength or frequency for the default settings. I will explain absorbance in a bit. At the upper left, we see the absorbing species. It defaults to carbon monoxide. I will change it to carbon dioxide for this video because this video is a supplement to my global warming main course. You might also want to try methane or water vapor. Many molecules and atoms are supported in this tool, whose use is not limited to Earth's atmosphere. I am selecting carbon dioxide. The plot did not change. We are configuring the settings for the next plot. The plot is not live. We will use the default database, HyTran, for this video, though I have also used the PNNL exsec to compare against an absorption cross-section plot. There is also HyTemp for temperatures hotter than Earth's atmosphere. So, HyTran database. I am setting the temperature to 288.1 Kelvin plus 15 degrees Celsius, being the Earth's global mean surface temperature. For now, I will keep the default pressure of 1 atmosphere, the bottom of the atmosphere. I will set the concentration of carbon dioxide to 420 parts per million, the value for 2022. I can enter 0.000420 or 420 E-6. The total pressure of the atmosphere broadens the spectra of the absorption lines, but the nitrogen and oxygen molecules do not add any absorption lines in the infrared ranges that we will look at. The next setting is length in centimeters. I will refer to this as cavity length L. The model is a fixed length of transparent tube filled with gas at a constant temperature and pressure. At one end is a source of light, and the other end is a detector, a spectrograph. The amount of light absorbed at a given wavelength is directly proportional to the length of the tube. In this video, the wavelengths will be infrared. We can set very large lengths, such as 100 kilometers. However, beware, the model is constant temperature and pressure. This model does not implement Earth's atmospheric profile. There is no gravity. If you set the length to 10 kilometers, you are not getting the result for 10 kilometers of atmosphere. Think of the tube as horizontal, not vertical. The default length is 1 centimeter, but I am changing this to 100 centimeters, 1 meter. Next, we set the wavelength or frequency range for the calculations and plot. We can either set the start and end wavelengths in microns here, or the start and end wave numbers here in inverse centimeters. Wave number is the inverse of wavelength. I will begin with the carbon dioxide range 13 to 17 microns, which is central to greenhouse warming. If you are doing methane, try 6 to 9 microns. There is also a step amount in inverse centimeters. I will leave the default amount for now, but will have to reduce it later. Now I click Clear Plots and then Add to Plot. And I got this plot in about 13 seconds. If you use a wide range or too small a step size, the tool may calculate for a couple minutes and then give you one of several errors. You can narrow your range and/or increase the step amount and try again. The vertical axis defaults to absorbance, which we will keep now. Later we will select transmission. The horizontal axis defaults to wave number in inverse centimeters, which this tool calls frequency. The frequency in hertz would be the speed of light times the wave number. Plots by climate scientists use wave number for the horizontal axis, with wave number and frequency increasing left to right. This tool also shows wavelength above the plot. In the main course, I used wavelength, so I will click Swap X-Axes to flip the plot horizontally, with the horizontal axis now being wavelength, increasing from left to right. Absorbance is a dimensionless positive number from 0 to infinity. We will use the letter capital A for absorbance. We can display multiple plots, each with its own settings and color, with legends at the upper left. Here's the legend. We can zoom in to a portion of the plot without adding a new plot. I will use these sliders to zoom in, but you can also use the other controls at the lower right. First, I will zoom in to the range 14 to 15.5 microns. to 15.5 microns. If you took the main course, this absorbance pattern matches the shape of carbon dioxide's absorption cross-section curve from PNNL, though the units are different, and the cross-section plot was a composite of 3 temperatures, 5, 25, and 50 Celsius, and 10 partial pressures of carbon dioxide. I want to know the absorbance value at the peak. I move my cursor such that the dotted vertical line intersects with the peak. And I get a little pop-up box that tells me about the value on the curve, or multiple curves if I have multiple curves. If you look at, I can't move my cursor, but if you look at that pop-up box, on the right there's a value for lambda, 14.980, and after that is the value of the absorbance, 4.64. The reported wavelength is not using full accuracy, and the simulation has a finite step size, so it may not match a different report of the peak wavelength. In fact, the last time I did this, I got the value 4.711 and a wavelength of 14.981. And that's what I'm going to use in the calculations. We can calculate absorption length for any wavelength. Take the cavity length that we used, 1 meter, and divide by the absorbance value, 4.711. For the peak, we get 21 centimeters for the absorption length for the peak. This agrees with the result from the main course. We can also compute the absorption cross-section, sigma, by dividing the absorbance, A, by the product of the cavity length, L, and the number density of the absorbing molecules, N, which we calculated in the main course as 1.07 by 10 to the 22 molecules per cubic meter at the bottom of the atmosphere for 420 parts per million concentration. Doing this calculation, I got 4.4 by 10 to the minus 18 centimeters squared per molecule as the cross-section at the peak. This is 12% lower than the cross-section value we estimated from the PNNL cross-section plot in the main course. But remember, that was for multiple temperatures and multiple concentrations. Now let's look at the valley wavelength, 14.1 microns. Absorbance is around 0.0022. So absorption length is around 455 meters at 14.1 microns at the bottom of the atmosphere. So almost 2,200 times larger absorption length than for the peak, but still smaller than the thickness of the troposphere. Now I want to show 2 new plots. I could clear plots, or I could scroll down and delete this plot, but instead I will click the status eye to not show this plot, to deselect it. You can only have something like 10 plots, so if the tool won't add a new plot, you may need to delete an old plot. Now I make one plot with length of 21 centimeters. I fast forwarded the video so you don't have to wait for the plot to be created. Notice that the peak absorbance is now close to 1. Here's the peak, and the scale is 1 there. This confirms that the absorption length is close to 21 centimeters. Now I make a second plot with length 20 meters, 2,000 centimeters. Absorbance increased by a factor of 100. Now we only barely see the first plot. We see this little bump here. Now I want to see which wavelengths have absorption length less than 20 meters at the bottom of the atmosphere. There are two ways to do this. The first way is to click Fix Y Max and enter the number 1. This has limited the absorbance to stop at 1. Now, all absorbance values larger than 1 are off the screen at the top. Go to any wavelength and see if we see the blue curve for that wavelength. If we do see the blue curve, as we do here, the absorption length for that wavelength is larger than 20 meters. For example, here at 14.880 microns. If we do not see the blue curve, because it is off screen, like here, it's off screen, the absorption length for that wavelength is smaller than 20 meters. For example, from here, 14.916 microns, to here, 15.005 microns, we don't see the blue curve. It's off screen at the top, and the absorption length is smaller than 20 meters. Notice that we see a lot more detail and complexity for the low absorption wavelengths with the longer cavity length, because it's been scaled vertically. Now let's try the second way. I change the y-axis from absorbance to transmission, and I unclick Fix Y Min if it is set. Transmission is e to the minus absorbance. The vertical axis transmission goes from 0 transmission at the bottom to 1 or 100% transmission at the top. When absorbance equals 1, transmission equals 0.37, around here, a little less than 0.4. That's e to the minus 1. When a wavelength has transmission less than 0.37, then its absorption length is less than the cavity length we used for that plot. For the Brown curve, here we see that the peak near 14.981 microns, it has absorption length close to the 21 centimeter cavity length we used, because the transmission value is around 37%, or at least less than 40%. Absorption, different than absorbance, is 1 minus transmission. This tool does not display absorption. So on the blue curve, the band from 14.944 to 14.988 microns has nearly 0 transmission and nearly 100% absorption for a 20-meter cavity. Now, let's remove the zoom and look at the range 13 to 17 microns again. 13 microns, 17 microns. I want to see what absorption looks like for the bottom kilometer of the atmosphere. I'm going to remove these two plots from the display by clicking their status eye at the bottom of the page. Then I add a new plot with length 1 kilometer. Remember, this tool is modeling constant temperature and pressure, not the atmospheric profile. It's a useful tool, but beware not to assume too much. We see a wide band of 0 transmission, 100% absorption, from about 14.3 to 15.7 microns. And there are partial transmission wings on each side. We saw this in the main course. As we continue to emit carbon dioxide and increase its concentration in the atmosphere, the absorption of these wings increases with concentration, and the 100% absorption band widens slightly. Thermal radiation from Earth's land and ocean surface gets absorbed by this carbon dioxide band, heating the atmosphere. The energy gets thermalized through collisions of molecules and then re-radiated in all directions as atmospheric thermal radiation. Radiation gets emitted by all of the greenhouse gases in the atmosphere, including water vapor. Some of that radiation gets returned to Earth's surface, heating the Earth's surface. This is the greenhouse effect. Recall that this absorption tool is not showing us thermal radiation by the gas, only absorption by the gas. Later, we will use the emission tool. We can save this plot to a file by clicking Save PNG, or we can save the data to process in a spreadsheet by clicking Save CSV. Now I will look at transmission through slices of different altitudes of the atmosphere. If this does not interest you, skip ahead to the section on emission. Now, I am going to delete all plots except for the last one, and add a transmission plot from 14 to 16 microns for the 10-kilometer altitude high in the troposphere, 223 Kelvin and 0.26 atmospheres. Now, only a narrow range around 15 microns is 100% absorbed by 1 kilometer of atmosphere at 10 kilometers. But a larger range, 14.5 to 15.5 microns, has absorption length less than 1 kilometer. Therefore, emissions from Earth's surface in this range will be absorbed before they reach the 10-kilometer altitude. Radiation in this range that reaches outer space comes from the 10-kilometer altitude or higher. Now I deselect the curve for the bottom of the atmosphere and add a plot for the 16-kilometer altitude near the bottom of the stratosphere, 216.6 Kelvin and 0.1 atmosphere, and show the range 14 to 16 microns. The 100% absorption range around 15 microns is narrower at 16 kilometers than at 10 kilometers. At all other wavelengths, transmission is higher at all wavelengths and absorption lower at 16 kilometers than at 10 kilometers. Let's zoom in to 14.5 to 15.5 microns. Now let's hide the 10-kilometer altitude and add the 50-kilometer top of the stratosphere, 271 kelvins and 8 by 10 to the minus 4 atmosphere. I know that this plot will be very spiky, so I am also decreasing the step size by a factor of 10. And now I'm adding the plot. This plot is much different. There is no longer a 100% absorption band around 15 microns. Now there are a lot of narrow absorption spikes, many of which have absorption length less than 1 kilometer because they're below the 37%, and some of which are 100% absorption. The low pressure at 50 kilometers has made the absorption cross-section highly spiky, not pressure broadened. This is why I reduced the step size. Had I not reduced the step size, the plot would have been wrong and I might not have known it. However, when we reduce the step size, we typically have to also reduce the wavelength range because the tool only allows a fixed amount of calculating time per plot. Now let's deselect the 16-kilometer altitude. Lots and lots of absorption spikes, many at 100% absorption. Radiation at some of those spike wavelengths that reaches outer space is probably emitted at higher altitudes. At other wavelengths where transmission is high at 50 kilometers, radiation probably reaches outer space from below 50 kilometers, even from the troposphere. Now let's add the 80-kilometer top of the atmosphere, 200 Kelvin and 1 by 10 to the minus fifth atmosphere. I want to decrease the step size by another factor of 5. I will have to reduce the wavelength range to 14.9 to 15.1. I'm going to zoom in to 14.9 to 15.1. Some of the wavelengths that had high absorption at 50 kilometers also have high absorption at 80 kilometers, slightly reduced. Here or here. But many other wavelengths that had high absorption at 50 kilometers have relatively little absorption at 80 kilometers, such as here. The change to low pressure and low temperature is complicated. Let's zoom in here. Here we see a red spike and a green curve that is a spike but also has a skirt to it and a valley, whereas the red just looks like a sharp spike. Radiation at these red spike wavelengths would reach outer space, having been emitted from the top of the atmosphere. Had we not reduced the step size, the plot would have been very wrong. Let's change from transmission to absorbance. Let's fix Ymax to 10. Absorbance is lower at 80 kilometers than 50 kilometers because of the reduced number density. But these red spikes still have absorption length less than 1 kilometer at 80 kilometers because the absorbance is higher than 1. But some of the spikes at 50 kilometers have no discernible spike at 80 kilometers. This may be due to the low temperature at 80 kilometers, but I have not researched this yet. The absorbance at the 14.98 micron peak is about 5.9 at 80 kilometers. Therefore, an absorption length of 169 meters at 80 kilometers versus 0.2 meters at the bottom of the atmosphere. Unfortunately, the cursor and its readout are unreliable when zoomed this much. So radiation at those red spike wavelengths that reaches outer space is emitted from the top of the atmosphere. The green spikes without visible red spikes are wavelengths that would escape from 50 kilometers and above. Let's enable the 16 kilometer and 10 kilometer curves and fix Ymax to 100. Here I have zoomed so we can see from about 14.85 to 15.01 microns. We can see how sharp lines at low pressure at 80 kilometers and 50 kilometers get pressure broadened at the higher pressures lower in the atmosphere, though temperature also affects absorption cross-section. So here we see a spike at 50 kilometers, the green spike, that broadens into the blue curve at 16 kilometers, higher pressure, which broadens into the brownish curve at 10 kilometers. Wavelengths in the valleys between 50 kilometer lime green spikes would escape from lower altitudes, but generally above 16 kilometers in this narrow wavelength range. At other wavelengths, radiation escapes from 10 kilometers and higher. Let's display only the 10 and 16 kilometer plots from 14 to 16 microns and fix Ymax to 1. From 14.5 to 15.5 microns, the 10 kilometer altitude has absorbance greater than 1, whereas 16 kilometers is both above and below an absorbance of 1. Radiation in the range 14.3 to 15.7 microns does reach 80 kilometers and escapes to outer space, but this radiation comes from different layers of the atmosphere. At the top of the atmosphere, the absorption at a peak wavelength can be more than 1,000,000 times higher than for the valley between the next peak. So absorption lengths also vary by 1,000,000 or more. The absorption length at the top of the atmosphere for the 14.98 micron peak is about 169 meters, so that wavelength escaping to outer space is emitted from the top of the atmosphere. But a nearby valley wavelength with 1,000,000 times less absorption escaping to outer space might be emitted from the troposphere. From the plot, we can crudely guesstimate that most of the radiation intensity that escapes to outer space comes from the upper troposphere and lower stratosphere. Very little to none from the lower troposphere, and none from the Earth's surface in this range. Recall that temperature varies with altitude, and radiated blackbody thermal emission varies with temperature, but also with number density in the gas. So the amount of radiated power escaping to outer space in some wavelength range depends on the temperature of the altitude where that wavelength has 50% probability to escape to outer space. You may want to think about this plot. You might like to see for yourself how 1.9 part per million of methane absorbs in the 6 to 9 micron range. Do you think methane wavelength emissions from the troposphere reach outer space and escape? Now we switch to emission. We go back to the top page, select emission, and let's start with blackbody. Let's enter 288.1 Kelvin for the bottom of the atmosphere. Let's enter the wavelength range 5 to 20 microns. We clear plots and Add to Plot. That looks like the wavelength version of the blackbody curve. The peak is at 10 microns. The values are given in watts per steradian nanometer meter squared. The value at 15 microns is 0.0058. The slope at 15 microns is negative because we are past the peak wavelength. Now we go back up and select Emission and Atomic Molecular Emission. Let's select carbon dioxide, then 288.1 Kelvin, then concentration of 420 parts per million. For now, we keep the cavity length of 1 centimeter. Let's enter the wavelength range of 14 to 16 microns. For now, we'll keep the step size. Later, we'll have to reduce it. We clear plots and add to plot. The horizontal axis defaults to what SpectraPlot calls frequency, which is wave number, 1 over wavelength. I want to change this to wavelength because that's what we've been using in the main course. But before I do, the values are given in microwatts per inverse centimeter, centimeter squared, steradians. These are the units for the wave number version of the spectral density. Now I swap x-axes, so the x-axis is now wavelength. But the vertical axis has not changed. This is still the wave number version of the spectral density, just flipped left to right. To get the correct values for the wavelength version of the spectral density, we must divide each value by the square of the wavelength. More on this later. This looks a lot like our earlier absorbance plot, but actually it is slightly distorted because it is the wave number version. Now I want to see what happens as I increase the cavity length. What do you think will happen when I increase it to 100 centimeters, 1 meter? You may want to pause the video and think about what you expect before you see the plot. The emission increased at all wavelengths, but not by a factor of 100 everywhere. The emission in the valleys did increase by 100. The emission at the main peak increased by a factor of about 22. The emission at the lesser peaks increased by a factor of 80 to 95. Can you reason what is happening here? And you may want to pause before I continue. This emission tool implements absorption as well as emission. A wavelength with higher absorbance value has higher absorption cross-section and smaller absorption length. The absorption length for the peak near 15 microns is 21 centimeters. Our cavity length is 100 centimeters, 5 times that absorption length. Most of the power emitted at that peak wavelength by the carbon dioxide in the cavity is getting absorbed by that carbon dioxide in the cavity and not escaping to the end of the cavity and the virtual detector. The cavity length is much larger than the absorption length at the peak wavelength, so the detected emission has saturated. The emissions at the valley wavelengths have not saturated because their absorption cross-sections are low and the absorption lengths are larger than this 100 centimeter cavity length. So increasing the cavity length by 100 increased their emission by 100 because there were 100 times as many carbon dioxide molecules to emit thermal radiation. You may want to pause and think about this. Now let's increase the cavity length to 10 meters. The emission value at peak near 15 microns has barely increased, but now the lesser peaks are also saturated for this cavity length. Now let's increase the cavity length to 100 meters. Now let's increase the cavity length to 1,000 meters. The red plot for 1,000 meters looks like a line. For the 1 centimeter cavity, the emissions looked complicated, quantum mechanical, and particular to carbon dioxide. But for the 1,000 meter cavity, the emissions now look like a black body. This is a complex interplay of emissions and absorptions. Now, there is a pesky issue to be addressed. If we use the cursor, we will see that this red line has positive slope. The value at 15.5 microns is higher than at 14.5 microns. Positive slope. But we know that it should be lower for the wavelength form of blackbody spectrum at this temperature. It turns out that when we divide these values by the square of their wavelengths, we get the correct blackbody values and a negative slope. I encourage you to think about this, do the math, and verify this. It would be great if SpectraPlot implemented a unit conversion here, but real users likely use the wave number form. So now we see how a thick slice of the bottom of the atmosphere looks like a black body emitted the radiation. Let's look at different altitudes. First, I will delete all but the last plot. Now I add a 1 kilometer slice at altitude 10 kilometers, 223.3 Kelvin, 0.26 atmospheres. Intensity emission has decreased due to the lower temperature. I encourage you to find the values at 15 microns, better yet 14.98 microns, and check them with Planck's law. And check the ratio versus the Stefan-Boltzmann law. The envelope of the 10 kilometer altitude curve still looks like a black body, but now Many narrow wavelength ranges are less than 100% absorbed in a 1 kilometer slice. So for this 14 to 16 micron band, most of the emission that reaches 10 kilometers is coming from that altitude, but some wavelength ranges have a fraction of their radiation coming from somewhat lower altitudes. For example, look at 14.5 microns here, and think about that. Now I deselect the bottom of the atmosphere and add a 1 kilometer slice at altitude 16 kilometers, 216.6 Kelvin, 0.1 atmosphere. The envelope again looks like a black body curve, and the emission intensity has declined a little due to lower temperature, but this slice is less absorbent than at 10 kilometers. More radiation from lower altitudes would come through. Now I add a 1 kilometer slice at altitude 50 kilometers, 270.6 Kelvin, and 7.87 by 10 to the minus 4 atmospheres. I expect this curve to be spiky due to low pressure, so I'm reducing the step size by a factor of 10 and narrowing the range to 14.8 to 15.1 microns. The 50 kilometer curve is spiky, not black body. However, the envelope of the tallest spikes would be a black body curve for 270.6 Kelvin, which is warmer than the 16 and 10 kilometer temperatures. Now I add a 1 kilometer slice at altitude 80 kilometers, 198.6 Kelvin, 1 by 10 to the minus 5 atmospheres. I will leave it to you to think about the 80 kilometer plot and these plots in general and the radiation that escapes to outer space. For radiation that escapes to outer space from different wavelengths in this range, from where in the atmosphere is that escaping radiation likely to have originated? I hope this video has been useful to you. You might like to watch the main course video on global warming and the video on methane.